Okay, let's begin. Homework on questions on the homework.
Are you going to test
We have
those?
homework for chapter 7 and 8, right?
Yeah.
Yeah. So let's start with chapter 7.
So there was something about finding the Q point on a range, estimating the quartiles, given bins.
Finding the what points?
Quartiles. 0 to 4.
Okay, yeah.
On bins, using bins or we never run it.
Oh, well that's the same, it'll be just like finding a median. Except, you remember how you found the position of the median?
Yeah.
Right, well that was just n over t, right? So if you want to find the position of, say, the Q1, what you do is that happens a quarter of the way. You divide by 4.
Oh.
And if you want to find the position of the Q3, that would be 3 over 4. Right? So you find those positions and then you continue just like you with the median.
Okay.
And you,
Huh?
Okay.
but
So you just identify the positions with these formulas. The median happens halfway point, Q1 happens at the quarter way point, and the Q3 happens at the 3/4 way point. Just find those positions and do the same bin spacing times step size thing. And find them just like the median. Remember, they are medians. They just, you ignore parts of it.
Okay. That's easier.
Other questions? 19. What does that say?
It says, suppose you obtain an average of 73 on 3 exams during the first half of the course. 5 exams are scheduled for the second half. What must your average be on the remaining 5 exams to produce an average of 80 for the entire 8 exams?
5 more exams.
You want an average of 80 for the entire 8 exams.
Okay, ideas?
So since we want it to be 80, we do 80 equals, I did 73 times 3, which gave me
And then I'll
219.
It says what grades do we need on the other 5? What average do we need on the other 5, right? So let x be the average for remaining 5. Then we want 80 is the average, so it's 80 is the sum of all your grades divided by the total, which is 8. Now I know we can assume that the first 3 grades are 73. That would give us 73 average. And then we want 5 other grades that have x as the average grade. So you just assume x is the average. So basically you have 3 times 73 plus 5 times x over 8, and that should give us 80. And then you solve for x, whatever x is supposed to be. So this means x equals whatever. Other questions? On chapter 7?
So your x is a decimal point?
Did you have to plug it in?
Your x is a decimal point? What's what I got? Decimal point.
84.2.
Oh,
How do you get a decimal?
never mind.
Yeah, you get 84.2.
Any other questions? No more chapter 7 questions? Chapter 8?
For 3C, did we have to draw the graph, or could we just write that it's going to be a bell curve?
What did 3C say?
3C said
Three C in this problem, problem 9.
Oh, no, no.
Problem 3C.
This is chapter 8.
Okay. Oh,
Says-
chapter 8. Okay,
yeah.
what was
Can
like
we use the
3A?
range rule from chapter 7 and the answer in B to estimate the standard deviation for each data set? State reason, the true values are S of X, the standard deviation of X is 2.1 and the standard deviation of Y is 4.2.
So it's okay, repeat the questions in exercise 2. So it says use the range rule.
From 8.1.
And we're looking at the data from 8.1. Yeah, so you'd have to draw the did it ask you to draw a histogram?
The histogram is fine, but then in C it just said to explain how the standard.
Yeah, so you do that based on how your histogram looks. So
So we don't have to draw the bell curve, right? Because I drew the.
no, but your histogram should look approximately bell curve. So you should have your histogram looks something like this, or something similar. The range rule, you can use it. But if it doesn't look like that, so if you plot your histogram and it looks something like this,
That's how it's for Y.
you can't use the range rule, right? It has to look like, if you connect the tops, it has to look like almost like the bell curve, which means the peak has to happen in the middle and it gradually slopes off on the ends. All right, so in that case, to use the range rule, you have to be approximately bell-shaped. So if your histogram looks like that, you can use it. If it doesn't, if it's skewed any other way, you can't. So that was basically the idea. So basically, after you draw the histogram based on what that picture looks like, you can say, yes, we can use the range rule, or no, we can't. And if you can't, you just use it. So it depends on what your graph looks like, which I don't know where to put it. Yeah, so to apply the range rule, you have to be bell-shaped, so your histogram has to look like that.
But then for question 3, how are you supposed to use the numbers that they give you to plot this? Because they only gave us what, standard deviation and means for 2 numbers.
I think they gave for that whole table. There's a whole table of data.
So what, we were just supposed to plug those numbers into the old table? That's why I was confused by the calculation.
No, in the chapter, there's a table 8.1 that gives you a lot of numbers for like 2 exams. That's on page. This. On page 139 is the data that they're using. So on page 139, you'd make up your own bins, create your own frequency table, draw your own histogram, try to get at least 5 or 6 bins. Yeah, so you're supposed to create your own table from the information on page 139. And once you actually do that and you make your histogram, then based on how that looks, you can sort of know what tricks you can use. There are some tricks that only work when you have a bell shape, curve shape, and some you have to use in general. Other questions? On chapter 8. And pass your homeworks up. We'll move on to chapter 9. Where we're going to do regression analysis.
The last time we had
Oh, yeah.
But something doesn't make sense. I don't know.
It's called regression analysis. So I updated the report cards with the second exam grade. The first exam grade should already be dropped, so yeah, a lot of you made a comeback, as I said, with the second exam. So now with the third one, I'm gonna have to like kill you guys.
Please
really,
don't.
really kill you, and then you can get back to normal. You can't have everyone passing. You just
Wait,
can't.
John.
You just can't.
Do you get like a rate?
So,
Wait, I thought CUNY doesn't follow that system.
what system?
Like,
What do you mean?
apparently
30%
you
need
have
to
drop-
fail.
You have to fail a certain percentage of students, and like a certain.
Is there anyone who follows that system?
Also, okay.
Clearly, you were trying to. You were all set for that system.
I don't know what you're talking about. I honestly don't know what you're talking about right now. Okay, so a wavy definition, basically. So remember we did scatter plots in chapter 7 or 8 or one of them. So a regression line, the line that we're after, is the line that, and we're going to explain what this means, best fits data points in a scatter plot. Right, so basically if you have like some sort of scatter plot here, dots all over the place, right? If you can draw a line where the distance from that line to all the points is as small as it could possibly be, so that's the line that's sort of as close to every point as you can possibly get, that guy you call a regression line. Regression lines are important because they're going to help us predict things. So here's some data set Y and here's some data set X. We want to get to a line that's as close to all points as much as possible. And we will use that to do predictions so that we can answer questions. Okay. So now how do we get to this? To get to this line, called the fitness. We're going to use a function that measures the average distance from the line to all the points. It uses what's called the method of least squares, which I shall describe presently. So the idea is, here's my regression line. There are some random points. I'm just drawing 2. So suppose that this guy here is our regression line. And it has the equation y is equal to a plus bx. Use the notation I used. Right. So now, if we measure the vertical distance between each point and this line, right? So here's one point called D1, D2, right? So I'm going to measure the coordinate from this guy, call this x1, y1, and I'm going to measure it to the point on this line, xy, which of course has the equation x comma a plus bx is the y coordinate. Similarly here, if this is x2, y2, measuring it to the point I'm keeping the x value fixed here, keeping the x value fixed here. So this would be x2 comma a plus b x2. Right? So this is my line. These are two random points. I'm sort of illustrating the idea. I want to measure the distance between these 2 points. And it's the vertical distance. And then what I'm going to do is I'm going to average them, kind of. My D1 here represents the distance here. Distance between x1 and y1 and the line, and this is the distance here. So no. That my D1 is going to be the absolute value between the points x1, y1 minus the line.
Yeah.
x1 comma a plus b x1, right? Which really is just the difference in the y values, if you look at it that way. So what would that look like? I take the difference in the y values, so it's going to be, the order doesn't really matter.
Oh my god.
y1 minus a plus b x1. It's a vertical line, so the distance between them is just the distance between the y values. We're going to use this to derive a formula for the fitness. Just want to make sure the notation is consistent with
Should
your
it
text.
be minus a minus dx?
What?
Should be y1 minus a minus dx.
I want this in brackets. Yeah, I wrote it the other way where I didn't need brackets. I actually subtracted the y1, but it's absolute value, so it doesn't matter. Okay, so now remember when you have distance formula, it's the difference between the points, you square it, and then you take the square root, right? You add them all together, right? Distance formula. Here, I don't want the square root or any of that, so I'm just going to measure it without the square roots. So this guy, I'm just going to throw the formula. So use distance equals, right, if I take all these d's and I square them and add them together, kind of taking inspiration from the distance formula, right? We get what I call the fitness to the point A, B. So I just plug in these values. So it's like a plus b x1 minus y1 squared, a plus b x2 minus y2 squared, a plus b xn minus yn squared. Sort of a distance formula approach. Right, so I created a line. I assume its equation is a plus bx. I measured the distance between that line on all the points. The distance between them on all the points would be whatever positive value this gives us. Right? Just take the distance. And then I take the sum of the squares of the distance, because you know that's the distance formula, except the radical. And I create this new function. Right? So now the line that best fits the data will have f of a, b, be as small as possible. Right? I want the average distance to be close to all the points as it can possibly be. However, much more than this I can't derive it because we have two variables here. You sort of need multivariable calculus, which we've never done. There are two variables to consider here. A, B. So we need multivariable calculus to find the limit, to find the minimum. Which is basically Calc 3. You guys haven't done it, so you're just going to have to take my word for it that this will all work out what I'm about to write down. Right, so the idea is you sort of like Calc 1, you find the critical points by differentiating, and then you find the maximum minimum. However, there are two variables to worry about at the same time. That actually makes things a bit sketchy. It's something that you do in Calc 3, but assume that this magic happens right here. I find the minimum of this function. What points A, B will make that function as small as possible. Now, doing that, we obtain the following that I'm about to tell you. And we will write it in a theorem. Are we done writing this down? Okay. So you won't need to know how to derive any of this, so don't worry about that too much. What you do need to know is what I'm about to write down. I just sort of wanted to show you an idea of what went into thinking about this problem.
Is that supposed to be your hat?
What?
Like, the line that best fits the data will go
The line that best fits the data will have this is a will. Yeah. This is an English class. Jesus. Sayana distracted me with her threatening books. She's always trying to threaten me. Suppose the regression line has this equation. Y equals A plus BX. Then there are a bunch of things that we can actually know about these values. For example, 1, my B will be equal to R times standard deviation of Y over standard deviation of X, right? Based on the formulas that I gave you in the last section, right? So this is just the covariance divided by the product of the standard deviations. These are the standard deviations of Y and X respectively. And that will actually give you your B coordinate. Right? 2, the line will pass through this point. The line passes through X bar comma Y bar, which is the average, the mean average of X and Y respectively. Right? So we can use calculus and we can figure out to make this a minimum, these things will have to happen. Our B coordinate must be this value, and the line must pass through the average point. Right? So if you're doing any of these guys, and you have dots all over the place, then that one dot that represents the average of X and Y, the best fit line will pass through that point. And its slope will be equal to R times Sy over Sx. So I know a slope that the line I know the slope of the line, and I know a point it passes through. I can find its equation. right? Just use the point slope formula, you can find the equation. Well, these two are very important equations here. This is very important, know this.
What's the slope? What does it say?
Slope is equal to this, the b. So I wrote slope is equal to r times, right, I'm saying here the slope of this line is equal to r times sy raised x. And the point it passes through is the coordinate of the means. And it turns out, I can't show you because it's multivariable calculus, but you can actually prove that this has to happen for that f function to be a min when you do calculus on it. We also have some notation here before I tell you the other thing. Often, if you look in statistics books and later on in this book, B is denoted by it's called B hat, B with a caret on it. It's really there to tell you about approximations versus real values, which later on that's going to be a concern. And A is denoted by A hat. And so later on in the book you might see them call it with hats. And in the other statistics book they'll put that little notch over it. You don't have to worry too much about what that is now. I just wanted to mention that notation thingy. This leads to another theory. If you know this term isn't as important to know, but I guess you might as well know it. Because if you know that, you know the slope of a line and a point it passes through, you can find the equation of the line. Right, so here's theorem 2 that tells you how to find the equation of the line, in case you forgot your algebra, which you shouldn't. The equation of the regression line is given by any of the following. One, we can use the slope formula. We know that b hat is equal to y minus y bar over x minus x bar, right? Just by using the slope formula. Do that, you solve for y. That will give you the equation of the line. Well, it's just multiplying this by that. Y minus y bar equals b hat x minus x bar. This is like y minus y1 equals m times x minus x1. And which, like I said, if you know this, you kind of know that. Can I get rid of this?
Yeah.
So for B.
This is the important thing to remember, I think. You really get this, that will fall into place. And 3. These are pretty much all rewriting the point slope formula. That's our theorem, and we have a corollary. Which is just a fact that we can deduce from this theorem. The y-intercept of the regression line A hat equals Y bar minus B hat X bar. So if you're like me, you don't like memorizing things, pretty much know theorem 1, and then y minus y1 equals mx minus x1. It's going to be the same thing. Let's actually do an example. Find the regression line for the 10 grades in our chapter 8 example. So remember in chapter 8 I gave you a list of 10 pairs of grades for exam 1 and exam 2. So if you plot those on a scatter plot, I actually want you to find the regression line. Recall some important numbers. These were actually computed before. So in an actual test, you would have to compute these yourself, but we already did this, so I'm just going to remind you of the values that we got. I think we got X bar was 73.5. Our Y bar was 73.6. Our standard deviation of the X values was 15.12. The standard deviation of the Y values was 14.08. We computed our R value, that was actually 0.766. So remember, you'd have to know how to compute these. So on a test, I might not give these to you. I'll just give you the data. You'll calculate these yourselves, and then I could actually define the regression line after. Right? So assuming we did all the work, we calculated all this, we know the means, the standard deviations, and we know the R values, how do I find the equation for the regression line? Okay, so what do we need to find the equation of a line? A point and a slope, right? So we know that B hat is equal to the slope of the regression line, and that's equal to R times S1.
766. Oh, never mind.
What?
Never mind. I was going to say.
R times Sy over Sx. Our R value is 0.766. Our standard deviation with respect to Y is 14.08. Standard deviation with respect to X is 15.12. When I put that in my calculator, I got 0.713 approximately. And then I know a point on the line. Let's say I call that x1, y1. That's actually just the mean. So that would be 73.5, 73.6. Which means regression line is given by y minus y1 equals mx minus x1. Y minus the y1 is the y bar, which is 73.6, equals the m is our b hat, which is 0.713. X minus our x1 is our x bar, which is 73.5. Or to write it in the a plus b I form, I got 21.19. Y is equal to 21.19 plus 0.713x. So again, forgetting all the theory and just jumping into the mechanics of solving a problem, I can give you some data. I can give you a list of values, right? Where they fall into two different categories, the x values and the y values, right? You have to compute the means, which you know you add all the values divided by the number of values there are. The standard deviations, where you do that full formula, the square root of the sum of xi minus x bar all squared over n minus 1. You get these guys. You get the r by finding the covariance and dividing by the product of the standard deviations. Once you do all that, which you have to remember all your formulas from chapter 7 and 8, then you just remember these extra formulas, right? The slope will automatically be given by this. Now, this you definitely have to memorize because to derive it requires calculus that you haven't done before. So that's just a definite, you gotta memorize that, right? And so this formula is what's gonna give you the slope for that regression line. So you just plug in the numbers that you found before. Got that guy. The regression line must pass through the point given by the means of the values. And so I have a point and a slope. I just use the point slope form and get the equation of the line that way. So this would be the equation of the regression line. So if I were to plot these grades, the scatter plot for these grades, so this represents exam 1 grade, and this was exam 2 grade, and they were like scatter plots. Then the equation of the line that's closest to all the points as possible would be y equals 21.19 plus 0.713x. That would be the equation of the line that best fits this data. That's pretty cool. Any questions on this so far?
So we don't need to know the distance stuff that you showed us before, right?
No, that was basically deriving to get to
Okay.
this. You need to remember theorem 1
And the theorem two.
and this, which you should already know. Once you do that, you can get to the regression line. Of course, you need to know how to find all the pieces in this formula. And yeah, just kind of plug into it.
Are we done with chapter 9?
Almost. There's one more thing. Yeah, chapter 9 was really short. Most of it was deriving all this. I just gave you the down and dirty version. Prediction. One use of the regression line is to predict values. The idea here is that because we're assuming this line is as close to all points as possible, we can sort of guess that if you give me some new x value that wasn't considered before, its y value would correspond to the y value that's on this line, right? It should be close to it.
Say that one more time.
I'm going to write it down. Given an x value, given a new x value, let's write it that way, we can, I want to say can, predict its corresponding y value. By using the y value from the regression line. it's kind of the same idea behind using a tangent line to approximate a function, right? So we're like, the tangent line is really close to the function, so we can sort of use that to approximate values of the function. It's going to be the same thing. So we'll just pretend that if I give you a new x value, like someone got another grade that I never considered before, could I predict what grade they will get on exam 2? I would say, well, I'd assume that their grade that they get on exam 2 will be given by the y value here, and so I can trace it across and predict it. So,
Can we do that with this class?
should I? Because I feel like exam 1 would skew a lot of things for you in the wrong direction. Exam 3, I already started planning it.
Wow. So you're planning on doing like a bell curve?
It keeps getting harder. Right now it's like too easy.
Wow.
Too easy.
Cross it out first.
Okay, so from the regression line. So, we can think of the regression line as approximating the average y value for a given x value. So you sort of look at it like, on average, if that's what the grade you got on the first exam, this should be your grade on the second exam. Okay, so let's actually do a problem here. Which usually if I have a problem on this on a test, like part A would be to compute the regression line, and then I'm going to say part B is to use it to predict something. Right, so here's another example. Based on your answer above, predict a student's grade on exam 2 given that he or she scored a 78 on exam 1.
So it would be y.
So, end of the semester, grades are due. I lost the final for one of the students. I'm like, holy crap, I gotta give him a grade. So I'm gonna be like, all right, let's do statistics on this, math. We're gonna set up a regression line. Well, if they got this on that exam, this on that exam, that should be their final. That hasn't happened yet.
But that makes it easy for
Thankfully.
you.
Yeah, lost the exam, don't worry about it. Just use a regression line.
I'll tell my friend about that. So that person should get
Right, that's the
76.
part that shines.
Yeah.
There's
76.
77.514.
Comeback, man.
Unfortunately, that doesn't work in my class because I kill people so much during the semester that they, on average, do better in the final than typical.
Yeah, we know.
What?
The
I
final
don't know.
is like the last supper.
Yeah. Like everyone else, on average, they do worse on the final than in the class.
get your
In my class, it's totally the opposite. I don't know what that even is.
It's because everybody waits till the last second and then they just study like their mind out.
Yeah.
And all they
But
do
you can't do that if I'm giving you a quiz every week, right?
Nope.
Yeah, so let's actually use it. We got that line. Y equals 21.19 plus 0.713x. Now x represents the exam 1 grade. those are my x values. And my y would represent the exam 2 grades.
Wait, so this doesn't predict exam 3, does it?
No, exam 2.
Just
It can only predict the variables that I've already mapped.
So let's say assuming you graded 15 quizzes, right? So then you get 5 more, then you can add it on to that, assuming exam 1 and 2 are the same.
If I graded what?
Let's say you graded 15 and then 5 extra people came in late, so you have to give them that out of, right? And so you want to add it to this. That's what you would do, right? But you can't predict these scores for exam 3.
No.
Okay.
Yeah. So the idea behind statistics is you assume that things will happen as they all have happened,
Okay.
right? So by studying the history of all this data, we know that 78% of people get this disease, right? You just assume that in the future, 78% of people will get that disease, right? You can't really predict a disease that hasn't happened yet, that we've never seen, what the percentages would be, right? So in the same way, I can't predict anything about exam 3. I have no data, no history about exam 3. So I can only use my prediction to talk about exams 1 and 2, right? So yeah, I have to have data on the thing I'm predicting already, right? Because we're assuming that things will happen in the future as they have sort of happened in the past. That's an implicit assumption. So yeah, so here, if student got, stop bullying me, sir. If student got a 78 on exam 1, then on average, they are expected to get y is equal to 21.19 plus 0.713 times 78, which was actually
77.514.
76.804.
76.
I used my iPhone calculator. See that fast? So quick.
On exam 2. So yeah, lost the exam, no problem. Just give them a 76. 77.
They got a C.
Or even better, create a makeup exam that's like super hard that they score a 20 on. And then you sort of get back into the way things are supposed to.
Add them to the 30% you're failing.
So like one more for the 30%. That's basically chapter 9. Chapter 9 is just about extending on chapters 7 and 8. So in chapter 7 we were studying just one set of data. In chapter 8 we studied 2 sets of data, which gave rise to the scatter plot. And then now we want to make predictions on this data, which is what statistics is all about. You want to make predictions, answer questions, right? So the regression line is a very powerful tool to do that. I gave you the formulas to find it, and once you actually find it, you can make predictions about it. Any questions?
No,
Hamza keeps asking me to ask the question.
I'll stop it.
Stop it.
What did you say? That's it for chapter 9 then.
That's what I'm saying.
Homework for that is due on Wednesday.
And we can go home.
Early dismissal.
Oh, man.
And now we're moving on to chapter 10, which is awesome. Because it's a totally different kind of topic. So we're going to have to switch gears mentally.
Should we just like leave that for Wednesday?
No!
Because I'm not.
We are forging ahead.
Here right now.
Chapter 10, probability.
I don't have a gear to switch, so
What?
you know, like when your brain is just.
Done for the day, man.
Introduction to probability.
What are you going to say?
Which sort of goes hand in hand with statistics.
I hate school. I'm too close to this camera to be talking about.
Usually the relationship is stats give rise to probabilities. Like probabilities is sort of your chances of something happening. So if you sort of say, oh, you know, by studying the data, I'm just throwing this out there, like 68% of people who smoke 2 packs a day after 10 years get lung cancer, whatever, right? That number, 68%, that number is called a probability. So you have this massive data that you do statistics on to sort of come up with a prediction, and then the predictions you can express in certain ways. When you express it in terms of a percentage chance of something happening, you're expressing what you call a probability. And so that's how these guys are set up. We need to know to deal with probabilities because it will naturally arise when you're doing statistics. Probably it wasn't invented to deal with statistics, actually. It was invented to deal with gambling, really. Yeah. It turns out that a lot of math that you do now, it was sort of invented on at the patronage of rich people who wanted to take advantage of the system. So when you're gambling, right, you want to know the chances of something happening, you know? What are the chances that I roll a 7, you know?
One of my friends just won $10,000 in a casino. He played like a dollar scratch-off game. I swear to God, he won $10,000.
Was it dollar scratch off?
Yeah, it's $1 and $2 scratch-off. And
We
he got
don't
10
gamble
back.
with
Okay, that's not.
Put it up on Snapchat, whatever. I was like, yo, let me get some. Nothing, man.
I'm talking about stuff where you actually do something, right? And you want to sort of figure out what your chances are, right?
Keith Robinson.
So a lot of these people who, for example, even play poker, right? There's a probability that you have a certain kind of hand.
Yeah.
Right, so when you're thinking about what your opponent might have, what is the probability of him having it, and what is the probability of you being better, you know whether to bluff or not, right? There's a lot of these things that goes into it. So a lot of this comes from probability, where you're figuring out the chances of something happening. And so it turns out that statistics also give you the chances of something happening in some sense, when you look at relative frequency. So yeah, probability will naturally arise.
So you just calculations in your head as you're playing. Do you do it?
No.
Is that what
I'd be
counts?
here, I'd be like in 21, I'd go to Vegas. You saw the movie 21?
Yeah.
I wouldn't be here if I could do that stuff in my head.
Is this like counting cards?
Counting cards involves probabilities, yes.
Isn't that illegal?
Illegal,
Technically
Shmigel.
not.
Doesn't make sense. How do they know you're counting?
What?
How do they know you're counting cards?
Cameras.
How do you
But
They
you're
can
counting
watch
in
your
head.
eyes. You
How do you
like,
count cards?
so if somebody puts down like
Again, they use probabilities. The chances of you winning a certain amount of games can be
who has what?
crazy, right? So if you play 21 10 times in a row and you win 9 times, they're like, the statistics says you're not supposed to win that often. And then they start to look at the camera. And they start to look if you're concentrating while on the camera. And they start to look at how excited you get when you win on the camera. And then you're like,
Wait, you're not allowed to concentrate?
Yeah, how does that work? Like,
Yeah.
what's the point?
You
I'm
guys
gonna
can watch
concentrate if
more
I'm
movies.
betting money.
Yes.
I'm gonna be focused. Like, that's my money on the line. I'm not gonna ever gamble, but if I do,
right, yeah. So think of it this way, right? If you actually know a strategy to beat the system, right? If it works, how are you gonna feel?
Like, alright.
Yeah, right? Like arrogance, right? As opposed to if you're just playing and you don't know anything and you won $10,000. Oh, look at Snapchat, right? That's what you're gonna do. So if you're watching on the camera, if you're watching someone on a camera, they win 21 blackjack games in a row, and they're like,
it's nothing. Like, what
very
if you,
suspicious. So what they do is they call the security guard and they beat you up and
what
try
if
to
you
get you
just say, like,
confess
I'm so
to
good
around
for
the
money, it's
casino.
nothing.
No, you know what you gotta do? If you're smart enough to start counting cards, you need to be smart enough to act like this is Christmas every time you win. You need to be like, yes.
Okay, let's get back to the topic.
You're such a clown.
The probability of an event happening are the chances or likelihood of it happening. Sometimes we get this from experimental data, i.e. statistics. Sometimes you sort of use it this sort of mathematical sense, which we'll talk about. A workable mathematical definition. Let A be some event, right? This can be, an event is just an occurrence of some type that you can define and quantify, right? So A could be the event that you get lung cancer after smoking 2 packs a day for 10 years, right? Then, the probability of A occurring is given by, here's the notation, you write P of A. That's the probability of A. You can think of this as a function. And roughly speaking, it's this, the number of ways A can occur divided by total number of possible outcomes. So one way in which we can just use some sort of a mathematical idea is, for example, when you're flipping a coin, right? There are 2 possible outcomes. You can get heads or tails, right? So if I say, what's the probability of getting a head when I flip a coin, right? It's going to be 1 out of 2. There's only one way you can get a head. It has to land on the side where the head is facing up. Yeah. There are 2 possibilities, though. It could land on heads or tails. So the probability, the chances of me getting heads when I flip a coin is 1 out of 2, a half, 50%. There's half likelihood, right? Now there are other times if you, and this will assume that it's a fair coin, it's evenly weighted, and getting a heads is as likely as getting a tails. Under those assumptions, this is a pretty workable definition. Otherwise, you can do it by experiments, right? You pay someone to flip a coin 10,000 times and see how many times a head comes up and how many times a tail comes up. And you put that over the total number of coin flips, right? You could have done that, right? So there are tons of ways to get to this number. Sometimes just by thought experiment, sometimes by actual experiment and taking statistics. But this is basically how you find the probability of an event happening. This idea, this equation is a very, very important equation to know. You'll be using it all the time, so you need to remember that. So that's a workable definition. Another thing, just a notational remark. Events are usually denoted by uppercase letters. Okay. Let's actually do an example. This is basically what it probably is, the chances of something happening. A lot of times we can use that equation to come up with a probability if we're not given the probability. Just assume all possible outcomes are equally likely to happen, and then you figure out the number of ways that what you're looking for can possibly happen over the total number of possibilities. And that gives you a probability, or at least a close approximation of a probability.
Is this related to NCR or NPR?
Ultimately, right, when we're going to want to be able to find probabilities in more complex scenarios, and sometimes this equation is not enough. So there are going to be scenarios when we're going to use things like NCR and all that stuff. Yeah. Which is usually, it arises a lot in things like binomial probabilities, when you kind of have 2 possible outcomes, like an on or off switch, right? The chances that this person has this gene or not, right? Things like that, right? We'll get to that. That's chapter 13, 14 Yeah, we'll get to that. But for now, let's work with this basic definition and let's do an example. That number should probably be higher, but whatever. Hey, polls, all right? No. It's not about a presidential candidate. It's a true poll. What? No, but it's definitely right. In fact, I think this should be like a 39. And then that one is Sienna, who's always threatening me. I feel threatened. She's looking at me right now. Look at that. Like she's going to hurt me. Okay. So I might ask you a question like this. I give you some information. What is the probability that if you randomly select one of these students, what's probably that they love me?
37.
Not just love me, love all uppercase.
87.4%.
I don't know what that means. But I have a professional obligation, so don't get anything.
87.5.
Where are the chances?
87.5%.
So now probably
Oh.
student loves all uppercase Jhevon, right? In addition, you could have said, let A be the event the student loves Jhevon. You write P of A here. This is equal to the number of ways this can occur divided by total number of possibilities. Right? So in this case, the total number of possibilities is actually the number 40, because I'm picking from a group of 40 people. So it's possible to get any one of these 40 people. This is 40. Number of students we're choosing from. Number of ways this can occur, according to the poll, it can happen 35 ways. So then the probability of this happening is just simply 35 divided by 40, which is 0.87. 0.875?
Yeah.
So this is 87.5%. There's an 87.5% chance that this event will occur in the land of probabilities. One thing I want you to notice is that obviously you can't have the number of ways a particular event can occur to be more than the total number of all possible events, right? You'll always have a number less than 1. This suggests event A, the probability of A must range between two values. It could be 0 if there's no way for a particular event to happen out of the total possibilities, or it could be 1 if every way is for something to happen in the total number of possibilities.
It's like when you get a p-value for an
Here they will never be outside this range. You do your calculations and you get a probability that's negative or it's bigger than 1, you made a mistake. Take this opportunity to read your syllabus so you know what that means, right?
No.
Blasphemy.
Someone's paying attention. Blasphemy. Well, not completely. It's a really bad mistake. Right, so it's in the list of mistakes that you should never make. Right, so the blasphemies are you don't divide by 0, you don't distribute powers across sums, you don't cancel across sums. Then the big mistakes are that ln mistake. You don't assume 1 over the integral of 1 over something, that's ln of the thing. And you don't, the r value always has to be between -1 and 1, possibly inclusive. Probabilities always have to be between 0 and 1, possibly inclusive. So those are just some values just you need to know that you never venture outside that window because it's impossible by the definitions that we're using. I forgot I planned to talk about this.
Yeah.
Some things to notice. Note. Probabilities are often not intuitive. Know the definitions. And follow them. Right? So sometimes you read, the thing is, a lot of these probability problems, they come in word problem form. And so to you, you might be thinking about, oh, that makes sense, right? There are many cases where it just won't work, right? It's not always an intuitive game, so be careful of using your intuition here. Here's an example, famous example. It's very famous at this point. It was mentioned in the movie 21, by the way. Which is a good movie. If you haven't seen it, you should watch it.
It is.
It's called the Monty Hall Problem. It appeared in a newspaper like way back, decades ago. And then, people could send in their answers to the newspaper. Turns out like tons of people got the answer wrong, even like some really smart PhDs, and there was like this whole controversy over the thing. It was amazing. That's what you had controversy over in like the 1950s. Right? Anyway, there was like this game show, which is kind of like who wants to make a deal, right?
Yeah.
So you have the game show host, and there are 3 doors that you can, there's a prize behind one of the doors, and they're like goats behind the other doors. Right? So there's a game show. A very famous game show at the time was the Monty Hall show, so it's named after that. And it was very similar. There's a game show. there are 3 doors. Right? Door 1, door 2, door 3. Behind 1 is a car. Behind the other 2 there are goats.
You get to keep the
You get to keep the goat. You want goat? You want goat?
Yo, that was low-key racist for my people. No, but
Talking to you.
in my country, goats are like worth a lot, so.
More than a car?
No, but I mean,
You know what? Get the car and sell it and buy tons of goats. I don't know. I would assume the goats would appreciate in value, right? You get milk and stuff from them that you can sell eventually. You'll get money back. The car's just gonna suck money out of your pocket. You know, you'd probably be like, I want the goat. The average American would want the car because we're consumers around here in these parts. Okay, so here's the thing. Game show is easy. All you do, pick a door. If you pick the door with the car, you get the car. You pick the door with a goat, you get a goat. Okay. Alba wants a goat, so her problem is like different from all of our problems. Okay, so for the average person would want the car, right?
Right, what's behind door number 3?
And 2 goats.
Right, there are 2 goats and 1 car. 3
not
doors.
like door 1.
Oh,
yeah,
okay,
it's not.
There's only one door with a
So I was
car.
like, why are you playing this game?
No,
You get to pick a door.
I would pick door 1.
Of course you would. That's so predictable. I know you would have picked door 1. And you win whatever's behind the door.
I hope I win the car.
Okay? Pick a door.
1.
Whatever you feel like, right?
Oh,
So now what happens? Here's the scenario.
33%.
After you pick a door, the game show host shows you what's behind another door. Of course, it's a goat. So now the game show asks you a question. Do you want to change your answer?
Don't change your
I would
answer.
agree with you.
Don't change your
He then asks,
It's like 1 or
This is like.
Do we need to take these notes?
no, I guess
We
not.
get tested on the process.
I should like you, yeah, I should.
I was like writing.
I'll test you on similar problems, so I guess you want to really get the idea of how you think through it. He then asks, do you want to switch? Finally, here's the question. Should you?
You shouldn't.
You may have time to switch it around, are you thinking?
No. Assuming that what's there in the beginning is always there. So you go like, you're Alba. I picked door number 1.
I don't sound like that, but okay.
And then the host is like, door number 3 is a goat. Do you want to change to door number 2?
No, I'm gonna stick with 1.
It's actually a probability problem.
Oh.
What is the best answer? How can you increase your chances as much as possible to win the car?
By switching.
Well,
By
first
switching or by staying with your original choice?
not
First it
gonna
was
matter.
33%, right? It was 33 out of all of them. And then, or
But
33.3.
since they
And now,
eliminated one goat,
one's
you can have a
gone.
car or a goat.
Yeah, so now it's
It's
50-50.
50%.
It's 50-50?
You go with
Yeah.
your gut feeling, whatever.
First it was 33 in each, right? And
There's
then,
what? What did you say?
Put it on the slide.
So funny when the shy girl in class finally talks. And then what did you say? Okay. Yeah, do you have this situation? There are 3 doors. You know there are goats behind 2 of them. There's a car behind 1 of them. You pick one. He shows you another one. There's a goat. Do you want to switch? Right?
No.
Do you want to make the deal or do you want to change your mind? What is the best option?
Stay.
Who says stay?
We're all wrong.
It doesn't matter.
Who has seen the movie 21? Okay, you guys aren't allowed to vote.
I forgot.
People who didn't see the movie 21. Who should stay?
I would.
Like, it doesn't matter if you switch the door or not. I mean, the car's not going to swap from door 1 to door 2.
But what's the higher?
What's the answer?
Huh?
The beginning
It's
you
not
have
going to
to-
change, so you stay, right?
It's
Y'all
the
really
same
acting
thing no
like you
matter
get in a
what.
It's
car.
not going to change. The goat, if there's a goat behind these two before he asks the question, there's still going to be a goat behind those two before he asks the question, right? What's the difference?
Type of switching. You say.
Right?
Stay.
You stay?
I'm
You switch.
You should switch.
Why do you think you should switch?
Because you have to add the probabilities.
Oh, so you don't trust the game rules. You're like, that guy looks like he's lying. Yeah.
I'm
You're
a
gonna change.
math teacher just
Give
like
me a
you.
logical reason why you should switch versus not switch.
There isn't.
Because isn't it, I don't know, it doesn't make sense, but at first you had a 33% chance of having this door, now your chance increased to 50, but that first door had a 33, now the second door should have a 50% chance? I don't know. Doesn't make sense.
I think it has something to do with those numbers.
I mean, just because it has a higher percentage does not change whatever's
Listen,
behind the door.
If it was 33%, all you have left is a car and a goat. It's 50-50. It doesn't matter if you switch it now. They
Well, your
just trying to
chances
like make you second guess yourself.
Increases if you switch,
You
no?
know what I'm saying?
Yeah.
Yeah, so like when you're on a test and you want to change your answer, do you change it or not?
No, you don't. You're never going to multiple choice.
It's
You're
literally
never
your gut
gonna
instinct that's telling
Your
you
first
to do it.
instinct,
Just
right?
do it, honestly.
Just do it.
You just gotta go.
You got
Turns
live
out,
life
yes.
with no regrets.
Yes is the answer.
You should switch.
From a mathematical, logical standpoint, your chances increase of winning the car if you switch.
Yeah.
Not intuitive at all, is it?
Test this out.
So you're like, no, you go with your gut instinct, man. Your first answer is always the right one.
My gut instinct was to switch though. We never
I'm
did
gonna
finish.
tell you something. No, hell no, I'm a fair.
I'm like, it's too many seeds.
There are actually tons of ways you can figure this out. Let's do, so yeah, so you want to play this game, you go to a mathematician. Hey, what do I do here? This is how probability started. Things like this. You wanted to write, how can I take advantage of a system that seems random, it seems chance, it seems like you can't make a difference, but maybe you can,
I got it.
right?
You know this millionaire who used to be a statistician. Now he built a computer that actually measures the weather, the temperature, and everything, and that actually increases or decreases the chances of a certain player winning.
What?
Based on previous, based on the history.
Oh,
Yeah,
that's
yeah,
fun
YouTube.
stuff.
You could find it on YouTube.
Yeah. Well, based on, is it correlation? Because, remember, you could buy ice cream.
He
and
has
you'd be killing
like
somebody.
100 different variations, and they increase or decrease, and that affects the winning.
It's interesting. I actually never heard of that. So let's say, let's do it by experiment. Like, let's say, without loss of generality, say you picked door 1, right? And say, let's actually write it up. What are the possibilities?
Door 1.
Let's look at all possibilities, right? We're going to use our definition of probability that we had before, the number of ways something can happen versus the total possibilities. What are all possibilities?
1 or 3.
Right? So let's C equal car, G equals goat. Pretend we're not Alba and we want the car. So here are the possibilities, right? I can have the car in door 1 and then 2 goats over here, right? Or I can have a goat here, the car's in door 2, and then there's a goat here. Or I can have goats here, and the car here, right? Now let's say say you pick door 1, right? I already wrote that, right? So pretend you pick door 1. These are all possibilities of how the things can be arranged, right? So there are 3 possible scenarios, right? In scenario 1, it's actually better to stay, right? If you stayed, you would have won the car. What if you're in scenario 2 or 3? You picked door 1, you picked a goat. He opens door 3, do you want to switch?
Yes.
If you say yes, you now get the car. Scenario 2, switching will get the car. Examine scenario 3. You pick door 1. He shows you door 2. It's a goat. Do you want to switch? Yes. You get the car. Switching gets the car. There are 3 possibilities in general, 3 total possibilities. There's only one of them in which it's better to stay. There are 2 ways you can get the car. You increase your chances by 33% if you switch, right? Not very intuitive, but mathematically, you have a better chance of getting the car if you switch. Switching gets you the car 2 out of 3 times. You might not have thought it made a difference, but it makes a difference. So, the moral of the story, don't rely too much on your intuition when dealing with these probabilities. Work out from the definition, go by, number of ways something can happen over the total possibilities, examine all total possibilities, look at the number of ways that you want to happen can happen, and use that as your guiding step. Right, so we'll write down some questions that you guys can think about. And we will actually go through next time. So these are going to be some questions I'm going to ask that you might think the answer doesn't matter or doesn't really change, but it turns out they do. And we will talk next time just about how.
Is chapter 10 homework due next time or no?
No, we're not done. We're not done with chapter 10. Chapter 9 is due though, but chapter 10 we're just getting started. Okay, so here's an example. Suppose a couple has 2 children. A, right? And I'm going to talk about this next time, the equal likelihood probability kind of thing. So we're going to assume the chance of them having a boy or a girl is 50-50. Technically this isn't true, experiments show otherwise, but whatever. We'll assume equally likely probabilities, right? So assume equally likely probabilities and answer these questions. What is the probability? What are the chances that both are girls? Okay. So your friend says to you, I have a friend, he has 2 kids. How much would you bet me that they're both girls? What would you bet? What's the chances? Here's another thing. B. If you know one is a girl, what are the chances the other is a girl? It will be a totally different answer. Now remember, they already had the children. Their sexes are determined, right? We know if they're a boy or a girl already. You just don't know, right? So if you think, what are the chances that they had 2 girls, or in the situation where you know one of them is a girl, but you're not sure of the other and you wanted to guess what the sex of the other one is, turns out it's a totally different answer from part A, totally different situation. Kind of like in here, where the fact that you knew one was a goat kind of changed the answer a bit. Not very intuitive, but mathematically speaking, it will happen. Here's another Here's another one. Now you might be wondering why it's different from B, but it actually is. C. What if you know not just one of them is a girl? What if you know the older one is a girl? In fact, you know her name.
They're unrelated things. Just because you had a daughter first doesn't mean that it's going to
Florida.
impact your second
What are the
child.
chances the younger is a girl? Would it be the same answer as part B?
Yes.
It's not.
Because you know her name. And she's the oldest child.
Don't trust your intuition. Use the rules.
Chances are not changing.
Chances. Probability. Yeah, so these people already had 2 kids, right? Now you're just betting on a couple of different scenarios, right? If you win the bet, you win $100. If you lose the bet, you lose $100, right? What are your chances of winning the $100, right? What's the probability that both of them are girls? If you know one is a girl, what's the probability that the other one is a girl? If you know the older one is a girl named Freuda, what's the probability that the other one is a girl?
What are the
All
chances?
3 problems have different answers.
What are the
We'll talk about them
chances?
next time. Think about it.
No, it doesn't. It's not the same gender.
That's what you could have said.
Think about it. No, stay in suspense until next time.